Hello, everybody, and welcome to practice number 3, live stream for Circuit Lab. Hope everybody's doing well. I see we have Mr. Dazi there, Mr. Agarwal. So let me just tell everybody hello. So we got about 3 viewers right now. We'll wait till we get a few more. While we're waiting, are there any questions after reviewing practice number 3? Hello, Savani. Okay, well, with the 4 of us, we'll just start right now. So practice number 3 focused on series and parallel circuits and creating batteries out of common household materials. We're really learning the purpose of the electrolytes, the anions, cations, and determining what's going to be the positive and the negative terminal. Was everyone able to create a battery out of common everyday kitchen materials? We've lost 2 viewers. Who is still on? Oh, wait, we've got some folks back. Oh, good, Mr. Dazi. So, Mr. Dazi, did you have any questions? So let's talk about creating. We'll start off with talking about creating it out of common materials. So if you think about it, the electrolyte is what allows the free flow of electrons, okay? So what you do is that you find something that's sort of acidic, like a potato. Another thing that you can pick is a lemon. Works really well. Another thing you can pick that works really well, and this is not to be an endorsement, is any type of soda, okay? Like here's a Coca-Cola. That is your electrolyte, okay? You'll notice that in car batteries, they quite often use sulfuric acid, okay? Again, you need something that's going to produce a lot of positive and negative ions, okay? Then what you're going to need is like in this case, materials that are 2 separate types of materials. So you'll notice that this one right here is the copper. This right here is the steel. Okay? They have to be different because basically the way those materials interact with that acid bath is different. And because these materials are different, there's actually a different voltage at each area. Okay? So, as you may remember from our last meeting, we've got our handy dandy $6 multimeter, which should do the trick. I'm going to turn it to DC voltage. And you'll notice that I'm also going to turn it to 2,000 millivolts, which is 2 volts. Okay? Flip the switch to on. And at first, I'm going to measure it between the 2 terminals. Make sure I have 0 volts exactly. And I have 0.00 volts. Very good. Now, I'm going to take our potato. I'm going to attach to the copper the white terminal. And then to the, hold on a second, I lost my other hookup. Hold on 1 second. To the other terminal, I'm going to attach the yellow. This is only done to make it easier for me to attach it to my multimeter. I then take the white terminal and I'm going to put it on the red lead, and I'm going to take the yellow, which is the same as the steel, and put it on the black lead. So what you'll notice here, okay, the yellow and the black, and I've now got 940 millivolts, okay, which is the same as 0.94 volts, okay? Now the best way, and the way you'll get the most, is the deeper you stick these in, the more contact they have, the better they tend to do. If they're nearby each other, the better they tend to do. But let's say I take out the copper and I replace it with another steel wire. Okay. Same exact hole. Now I'm going to hook it up together. And you'll notice that the voltage sort of jumps around from all over the map. And then when I hook it in together, I get about 99 or 100 millivolts, so 0.1 volts. There's still some amount of voltage there, but it really is not much. And it's well within the error of this multimeter. So what that tells me is that there's not enough difference in the electron affinity of the two materials. And that's really what you're trying to do, is that you want to pick two materials that have as different of electron affinity as possible. Okay? We can do the same thing with a lemon. Okay, so I take out my electrodes out of here. I stick them in a lemon. Okay. Real quick, I put steel in one side. What should I put in the other side? If I want to make a battery, should I put the copper or the other steel? Please answer. Bonus points to whoever answers first. I get a copper with a question mark. Any other answers? Okay, well, we're going to go with what Mr. Dazzy suggested, and we're going to put copper in the other one. Okay. So now I'm going to make the same measurement as what I just made before. Okay. Now remember, we got about a volt out of the potato. And that's a pretty big potato. Remember, it varies how much you get based on the difference in the electron affinity of these two materials. And it also varies on the type of material. So let's see which one makes a better battery, a potato or a lemon. So if I take my potato or my lemon here, and now I hook it up here. Let's see what type of voltage I get. I get about 987 volts, so very close, almost a full volt, maybe a little less. I've generally found that I tend to get a little bit less with a lemon than I do with a potato. I'm not exactly sure if that's because I've got less in a potato than I do in the size. But generally speaking, I can get more out of a potato. Also, the potato tends to make less of a mess. So now let's do one out of a Coke. Okay. Now, by the way, if you ever do this, never drink the Coke afterwards. So I'm going to pour the Coke in here. Okay. And this is why you're never going to want to do it, because it's going to leave a really metallic taste to it. And, let's face it, licking these materials is not the best idea under any circumstances. I'm going to try to get it completely filled up here. Again. And so again, let's see what type of, let's see how good this battery is as battery acid for us. So we go from 0 to 1.03. So this is actually even better than the potato. Okay. And you'll notice what will happen is if I let these guys touch in between, it goes to 0. So you got to keep them separated. Okay. But it's about a volt. Now, I can't tell you enough, after you've done this, do not eat or drink any of the materials you've used. So don't eat the potato, don't eat the lemon, don't drink the Coke. Okay? Does that make sense to everyone? Okay. Now that we've got 5 people on, the first thing I'd like for everybody to do is we're going to do a binder check. So everybody get your binders ready. And I'm just going to show you how you can do a binder check, and you can do this with your coach. You can do this with your teammates. Yes, it was basically Coke gave a little bit better of a battery. It was a little bit better battery acid than the potato, which was a little bit better than the lemon. Okay, I would suggest everybody try it at home. Okay, and try some other materials. You can find a lot of materials online: vinegar, wine. Be careful with wine, of course, but I'd probably stick with the vinegar. Okay. Yes, water would be a very good one to try with. Okay. There are excess ions, so it's not going to be 0, but it's not super acidic, so it doesn't have a ton of excess ions in it. So it's really not going to, especially deionized water would not do well. That's a great one to try. Now, by the way, on the old days when you used to have to fix a battery, if you didn't have battery acid to put into your battery when it would burn it up, usually the water had boiled off from all the charging. So you would just add water in your battery. It was incredibly dangerous, and a lot of people made mistakes, and the battery acid was splashing their face, and it was very, very dangerous. So that's why pretty much all batteries are now sealed. So what was the measure I used? I used, that was millivolts. So 987 millivolts will be 0.987 volts. And it was DC voltage, yes. Yes, there are no AC lemons out there, at least not yet. And there are, all of this is going to be DC. Okay. So is everybody ready for the binder challenge? Now, the way this is going to work is I expect all 4 of you to type in as quick as you can when you find something that I shout out. I'm expecting everybody to chime in within 10 seconds. All right, is everyone ready? Okay. The first thing I'd like you to find in your binder is I want you to find the rules. Go. Very good. Beep. Okay, so we had 2 people who found it. Everyone else didn't. Or excuse me, Mr. Katz, I'm afraid you're a little late. Mr. Agarwal, I'm afraid you're a little late. Okay? You need to be able to find those things quicker. Okay? Mr. Dazzy, don't feel bad. Just make sure that that's one of the key things that you can always find are the rules. 1 page, you print them out, you can find your rules. By the way, that's going to be the same for every last binder event that you found there. Okay. The next thing I would like you to find in your binder is Ohm's law. Go. Okay, very good. And beep. Okay. Mr. Katz right under there. Mr. D, very close. Okay, again, try to find that very, very rapidly. Okay. The next thing I'd like you to find in your binder, and I'm giving you 10 seconds to find it. And right now, only 2 people have been able to find stuff very rapidly. I want you to find the electrical conductivities of materials, or the resistivities, either the conductivities or the resistivities of materials. Go. Very good. Very good. And beep. Okay, so we only had a couple of folks find it. Okay. I would like you to now find the equation for figuring out the combined resistance in a series. Go. Very good. Very good. Very good. Beep. Anybody else? Those of you who know me know exactly what I'm going to ask for next. I'd like you to find the equation for equivalent resistance for parallel. Go. Very good. Very good. Very good. Beep. Okay. Very good. Listen, even if you're finding it a little later, that's okay. That's why we keep practicing. If you're having problems finding some of the key things, my recommendation is look at how you're tabbing things, making sure that you can find the things that you need to find quickly. Okay. I would like everyone to now look in their binder and tell me when Mr. Ampere lived. I'm actually going to look it up online. We'll see who's faster. Okay, type in the answer. He made it to 61. The answer is 1775 to 1863. Okay. The reason why I use Mr. Ampere, he's definitely one of the ones that would count. And by knowing what time period somebody lives in, you can tell if they invented something during that time period. Okay. So who here had Mr. Ampere's historical information in their binder, or who did not have it in their binder? It's not a problem. Remember, we're not at competition yet. Did anyone not have Mr. Andre Marie Ampere's information? Okay. That's a big one. Okay. So make sure that you got the major people included. Okay. Another common one that I fully expect, which would be history-wise. No, it does not say only Volta, Tesla, Hertz, and Faraday. It does not. Okay. What it says under 3DI is historical perspective of the discoveries of electricity and the key people involved. So Ampere would be a key person involved. Okay. So I'm now going to ask you, when was the transistor invented? Got a 1947. That is correct. Now, they don't know exactly when. It was either sometime November 17th to December 23rd. I guess they took time off for Christmas. That's when John Bardeen and Walter Bratton at AT&T Bell Labs. Okay? So the thing I want you to keep in mind is that sometimes it's going to be stuff like that. Okay? So it's important to have as much of a list there that you can quickly find things. Okay? So that's the type of binder check I would normally do with my team. Okay? Now, in practice number 3, we went over series and parallel circuits, and we finally combined the two. Okay? And what we meant by combine the two is that means that not everything is going to be just resistors in series or just resistors in parallel. Sometimes they'll be quite complex. And so the key thing is you have to recognize what's in parallel so you can combine those things. You have to recognize what's in series so you can combine those things. And quite often what we're looking for is the overall combined resistance. So I'll go back here to our homework generator. Okay, so if I look here at our homework generator, okay, in this particular case, we have 2 resistors in parallel. In this particular case, if I've got 2 80 ohm resistors in parallel, I know by my little simple trick of the book, what should the R equivalent be? Go. Quickly. You do not need to calculate it. I've got 2 resistors. What's the R equivalent? So as you may remember, if you have 2 resistors in parallel that are exactly the same, you take the number of resistors and you divide them by that number. So R1 and R2, if they're both 80 ohms, if you put them in parallel, the R equivalent should be 40 ohms. Does that make sense? Very good. Okay. So it should be 40 ohms. Now, our battery is 400 volts. So if I got 400 volts and I got 40 ohms, what is I sub T? You know, in other words, the entire current coming out of the battery. With 400 volts and 40 ohms equivalent resistance. What's I sub T? Okay. Very good, Mr. D. So we take V equals IR, or I is equal to V divided by R. So that's 400 volts divided by 40 ohms is equal to 10 amps. Okay? Now, we also gave you the equation for power. Okay? So the total power coming out of this battery is equal to what times what? Please write it down. What is the total power coming out of the battery equal to? V times I, that's correct. So if I look at that, my V is 400, My I is 10. So that's 400 times 10, which is what in this particular case? What is V times I for the entire system? I got a 4,000. Okay. Here's the question I have for you. What's the unit? It's 4,000 what? Watts. That's right. 4,000 watts. Correct. Okay. So you've done a really good job. Now, what is the voltage across R1? You do not need to calculate it. What is the voltage across R1? If our voltage is 400 volts from here to here, so this is 400 volts. Remember, everywhere here is 0, and everywhere here is 400 plus that. So from here to here is also 400. From here to here is also 400. That's what makes it a parallel circuit, is that the voltages are the same. So the voltage across R1 is 400 volts. The voltage across R2 is also 400 volts. Now, what we'll notice is that the individual currents here, that would be 400 volts divided by 80 ohms here, which would be 5 amps. And I'll also notice I get the same thing here. 400 volts divided by 80 ohms is equal to 5 amps. And this makes perfect sense because if I got 10 amps coming out of here, it's split evenly because these resistances are the same. So the current will be the same. So therefore, 10 divided by 2 is equal to 5 and 5. And then they combine down here. And when you're coming back in here, we got another 10 coming back in here, even though we had 5 and 5. Did that make sense? Or did I lose anyone? Okay. Okay. So that means that that's how we solve parallel circuits. Very important. So that was level 2. Now let's go to combined. So you'll notice here that for the combined circuits, okay, we've got R1 and R2, okay, and then we've got we got R1 here, R2 and R3. Okay. R2 and R3 are what to each other? Are they series to each other or parallel to each other? Please type in the answer. Mr. Dassey. Okay, I've got one thing saying that R2 and R3 are in parallel or series to each other. Okay, how about Mr. D? Mr. Agarwal? Tripathi? R1 and R2 are in series, okay. But I'm talking about R2 and R3. Okay, I got parallel. Anyone else? Any other answers? So if I look at this, R2 and R3 are in parallel. The voltage across them is exactly the same, and the current is split. R1 is in series with both of those. So when trying to solve this problem, which two resistors should I combine first? Should I combine R1 and R2, R1 and R3, or R2 and R3 together first? Which should I combine first? Write down the names of the two resistors that should be combined first. Anyone? All right. Mr. D says 2 and 3. He says these two. Anyone else? Everybody's being real quiet. Okay. Mr. D was correct. And he's getting all the bonus points, by the way, because he's the one who's answering. That means that he probably prepared a little bit better. I expect folks to prepare, and I expect people to answer. Even if you don't know, type in "you don't know." Being quiet doesn't help anyone. Okay? So when you have a combination circuit, you need to combine the parallel elements first. So I would combine R2 and R3 together. Then I've got the combined resistance in series with R1, and I would combine it with that, and then I find my overall R equivalent. So the first thing you do is you combine the parallel elements, then you combine the series elements. Okay? Does that make sense? You can say yes or no, but I expect everybody to answer. I should see 5 answers. Yes. Yes. Okay. I should see 3 more answers. Yes. 2 more answers. And it's okay to say, I'm not sure. I just need to know if I can go to the next topic. Tripathi, are you still there? Agarwal, are you still there? Okay. I'm going to ask everybody to please type in responses so we don't spend time waiting for everyone to respond. Even if you don't know the answer, that's okay. So what we want to do is we want to combine R2 and R3 together. Now, if R2 and R3 are 20 and 40, real quickly, they're combined. What should that be? Come on, let's try to type that together. So we're combining 20 and 40 together here. What's that equivalent resistance? And while you're doing it, I'm going to actually do it on my calculator. Okay, 13.3, Mr. Katz is correct. Okay. The way I did it very quickly was I took 20 times 40, which is 800, and divided it by 20 plus 40, which is 60. Okay. Now, if 13.33 is my equivalent, and R1 is 30 in series, what's my overall R equivalent for both the entire circuit? Okay, again, Mr. Katz is correct, 43.3. I took that 13.33 of these two. It's in series, so 13.33 plus 30 is 43.33. Very good. Now, What is the current going through I1 or the current going through the battery? Go ahead. What is the current? 1 amp is correct. By the way, that's a rounding error, so it's just 1. But you'll notice that's 43.33 divided by the R equivalent, which is 43.33, is equal to 1. So that's 1 amp. Okay? Then, when you're figuring out the voltage through each one, you can figure out the voltage here, okay, is equal to that 1 amp times R1. So what is the voltage across R1? What is the voltage across R1? Okay, Mr. Katz guesses 30. Okay, so if I've got 1 amp going across a 30 ohm resistor, V equals IR is equal to 30 times 1, which is 30 volts. Very good. Very good. And by the way, I appreciate, Mr. Katz, you adding in the voltage. So if this is 43.33, this is 30 volts right here. What's the voltage from 2 to 5, which would be VR2? This one should be pretty easy as well. This is 43.33 volts. This is 30 volts from here to here. So what does this have to be? If you don't know, it's okay to type. That's correct, Mr. D. 30 plus 13.33 is equal to 43.33. So it's got to be the resistance or the voltages here have to add together. So this is 13.33. Very good, Mr. D. Okay. Very good, Mr. Diassi. All right, now let's do from 3 to 4. What is the voltage there? From 3 to 4, okay, or the same voltage across R3. What is it? That's correct. They're in parallel, so the voltage is the same. So the voltage from here to here is the same as the voltage from here to here. Same as the voltage from here to here, okay, from 2 to 6. It is going to be 13.33. Very good. Now, what's the current through R2? What is the current through R2? That is correct, Mr. Katz. 0.6665. Okay. And by the way, as a general rule, about 3 significant digits would be more than enough, but that's correct. Now let's figure out what the current is here across R3. And that is correct, Mr. Katz. It's 1/3. And this makes perfect sense if we think about it. Basically, we're saying that through R3, we're getting 1/3 of an amp. Through R2, we're getting 2/3 of an amp. And when they combine 1/3 plus 2/3, we get 3/3 or 1 amp. That makes perfect sense. So it all adds up. Now let's think about it. Does it make sense that I got more current going through R3? Or excuse me, less current going through R3 than R2? Yes, it does. It makes perfect sense because R3 has got more resistance. Okay, so therefore less current would go through. And since it's got twice the resistance of R2, I should expect twice as much current to go through R2 as through R3. So therefore, it makes perfect sense that this is 2/3 and this is 1/3. Now, the reason why I do it that way is that you should always sort of double check yourself and ask yourself the question, does it make sense? Like, did it make sense when you combined 20 ohms and 40 ohms together in parallel and the number was less than 20? Absolutely. The number should always be less than the smallest resistance. Just like when we added them together in series with R1 and it was 30 ohms, it wouldn't have made sense had whatever number we came up with been less than 30 ohms, because when you're adding them in series, it's always going to be greater than whatever your biggest number was. Okay? So what I want you to do is I want you to do level 1 in the simple series, level 2, simple parallel, and level 3, simple combination. Do those sheets again and again until you get all the numbers right. Make sure you understand how all the power adds up as well. The power of each individual resistor adds up to the overall power of the battery. So make sure that that matches, okay? Now we also, when we talk about power, we'll talk about impedance matching quite often. A lot of times, especially later, we're going to be designing circuits that will have a certain impedance because we want to drive some type of load. A very common thing to use is an 8 ohm load. I don't know why they picked an 8 ohm load. That's probably a good thing to look up on the internet. But generally speaking, most speakers are either 8 ohms or 16 ohms. And so when you're trying to drive a speaker, you want to have an internal impedance that's the same as that speaker. So you always want to have 8 or 16 ohms. Okay. And so it's not uncommon for us to want to design a circuit that'll have an equivalent resistance of either 8 or 16 ohms. And the reason why you want your internal resistance to match your load resistance is because that is where the you get maximum power transfer. Okay. And the reason why is that it gives you the highest V times R when those resistances are the same. Because if the resistance is too high on the load side, you don't get enough current. If the resistance is too low, okay, you get all this current, but your voltage goes down. Does that make sense? And so those were all the topics we wanted to cover with practice number 3. I want to apologize that I did not get practice number 4, the verbal versions. The slides are still available, but I'm going to do that tonight, and I'm going to try to do practice number 5 here soon. I'm going to try to stay a couple of weeks ahead, but feel free to go ahead and work ahead as long as you can handle the homework. If you can't handle the homework, like in this case, if you hadn't already tried to make a potato or a lemon or a Coca-Cola battery, then you need to do that before you go to the next topic, okay? If you can't do like level 1 series, keep doing that sheet until you're really good at it. If you can't do level 2 parallel, keep doing it, okay? That's why the sheets are set up the way they are. For those of you that are having problems with your binder checks, make sure you work on your binder, because I'm going to have a binder check at the next live session. Your coaches are going to have binder checks. Okay, are there any other questions before you guys get back to studying all your other subjects? Okay, well, with that, I guess we didn't have any additional questions. We will see you again next week. Remember, if you've got questions, please bring them right at the beginning of the session, and I'll answer them straight up. Take care, and I wish everybody the best of luck. Take care. Goodbye. Wait a second. Mr. Katz had one last thing. Sorry to keep bringing this up, but the rules say we need to research historical perspective on the electricity discoveries made by Volt, Ohm, Tesla, Hertz, and Faraday. Hold on a second. That's not what my rules say. Let me see which one of us is looking at the right rules. So what I'm going to do here is I've gone to the national website. Okay. We go to the national website. We'll go here. I'm going to go to the shop, to the SO store. Okay. I'm going to do the digital rules manual. I got to agree to the terms of services. Okay. Oh, I say, I gotta give them an address. Okay. So let's look at this. So we're going to bring up the B manual first. And we're going to go down to Circuit Lab, which is actually going to be page 6. Historical perspective of the electric discovery by Volt. I am wrong. I had an old version of the rules. So you remember how I told you to always make sure that you have the latest version of the rules? I failed that. I actually had the rules from this summer. Okay. I thought they hadn't changed. I was wrong. If I was an event supervisor and you had those rules in your book, guess what? I'm asking questions about transistors. You can turn around and tell me that I don't know what I'm talking about. Okay. So way to go, Mr. Katz. Well done. And that was exactly the right way to do that. You remember how we talked about bringing stuff up in a respectful manner? You brought it up in a respectful manner, and then you showed me the rule. You said 3 CI. And then I looked at it, and 3 CI was exactly correct. So what I'm going to actually do is I'm going to print this version out. And I am going to actually, this version, you got an old version of the rules, throw them away. You don't want to ever accidentally think you got the right version of the rules. Okay, so I had the wrong version of the rules. And so next time, I'm only going to ask you questions about Volta, Ohm, Tesla, Hertz, and Faraday. I will not ask about Ampere, and I will not ask about the invention of the transistor. And by the way, you just found an error from a national event supervisor. So well done. And you did it exactly the right way. Can I do designer genes? No, I am horrible at biology. Horrible. However, if you're interested in us doing a designer genes version, I'll actually reach out to nationals and see if they can have somebody do something like that. But I promise you, Bendra, you're better than me. You're better than me. I can barely remember how to figure out, like, I think if somebody's an A blood type, they have A and O in them. And if they're O, they only have 2 O's. That's the level of genetics I can handle. There are no live streams right now for any other events. However, if you're interested in those for physics events, I'm more than happy to do these for physics events. Honestly, as an engineer, I'm really only comfortable doing those. If it's some of the device ones, let me know. I know a lot of those folks, but like for designer jeans, what I'm going to do right now is I'm going to actually tell them, hey, we had a request. I'm going to send that out to nationals. I like that. You learned it from Jurassic Park. Very good. All right. Any other questions? Okay. Thank you all, and I will see you next week. Good luck.